The equations that we use for one-dimensional motion assume that the object is experiencing a constant acceleration. However, we can still use these equations if the object does not have a constant acceleration if we divide up the situation into phases where the acceleration is constant. As an example, consider the following problem. A motorcyclist starts from rest and accelerates at a rate of 4.53 meters per second squared for 5.31 seconds. He then spots a deer on the road, 105 meters from the original starting point. After 0.115 seconds of reaction time with no acceleration, he hits the brakes, slowing down at a rate of 7.83 meters per second squared and coming to a stop. And we are asked a number of questions about this situation. How fast was he traveling when he saw the deer? How far does he travel during his reaction time? How long does it take him to come to a stop? And if the deer does not move, will he be able to avoid hitting the deer? This is a situation where the acceleration is changing. In fact, we can identify three distinctive phases in the motorcycle's motion. First off, we have the speeding up phase where the acceleration is 4.53 meters per second squared. Then we have a reaction time phase when the acceleration is 0. And then finally we have a third phase slowing down with a deceleration rate of 7.83 meters per second squared. We can solve the problem by therefore dividing the problem up into three distinctive phases, each with its own acceleration. Now, of course, an important step in this problem-solving process is always to extract the data from the problem. That can be done in the form of a data table, as we've done before. I want to show you how it can be done with a diagram. So here we have a diagram of the motorcycle's motion showing the three distinctive phases. Phase 1, where the motorcycle is speeding up with an acceleration in this diagram to the right. Then we have the middle phase, the cruising phase, the reaction time phase, where the acceleration is 0, but we are still moving to the right. Then we have the third phase, the slowing down phase, where the velocity is to the right, but the acceleration is going to be to the left, causing the motorcycle to slow down. So we note what the acceleration is at each of these three phases. We also note the velocity at certain key times, the velocity being 0 at the beginning, some intermediate velocity at the end of phase 1, another intermediate velocity at the end of phase 2, and then, of course, the final velocity, which we come to a stop, that's 0. We also note the position of the motorcycle, the starting position, which for convenience we will call 0, the position of the motorcycle when the driver spots the deer, the position of the motorcycle after the reaction time when the motorcycle begins to slow down, and then the final position, which we will compare to the position of the deer 105 meters from our starting point to see if we hit the deer. Finally, we can fill in some times here. We know the time to accelerate. We know the reaction time. And finally, we do not know how long it takes the motorcycle to come to a stop. So we divide the motion of the motorcycle up into these three phases, each of which has its own distinctive acceleration. The key to solving this problem is to realize that the final velocity of phase 1 is the initial velocity of phase 2. And the final velocity of phase 2 is the initial velocity of phase 3. And the same goes for the positions. The final position of phase 1 is the initial position of phase 2. And the final position of phase 2 is the initial position of phase 3. Therefore, these phases are linked. So if we can kind of start a chain of solutions working our way down the diagram, we can ultimately find this final position and answer the last question. But let us address the preliminary questions that are asked. First off, we are asked, how fast was he traveling when he saw the deer? This question is asking for the velocity at the end of phase 1. Well, that can be found very easily using the first kinematics equation, which is v final equals v initial plus acceleration times time. In this case, the final velocity we are calling v1. The initial velocity is v0. The acceleration is the acceleration during the first phase, and the time is the time during the first phase. Well, now we can plug in our numbers here from our diagram. v1 is our unknown. v0 is 0. A is 4.53. The time is 5.31. So we can easily find that the velocity at the end of phase 1 is 24.1 meters per second to 3 significant figures. We can also do another calculation here to determine the position of the motorcycle at the end of phase 1, in case that might come in handy, using this kinematics equation. Final position equals initial position plus initial velocity times time plus 1/2 times the acceleration times the time squared. Again, we go up to our diagram and find the relevant variables. The final position is going to be x1. The initial position is x0. The initial velocity is v0. The time is t1. The acceleration is a1. And again, the time is t1. Plugging in the numbers that we know, the equation gets very simple because a lot of the quantities are 0. We come to the last term where we put in our numbers for the acceleration and the time, and we get that the final position at the end of phase 1 is going to be 63.9 meters. All right, so we've determined that the velocity at the end of phase 1 is 24.1 meters per second, and the position at the end of phase 1 is going to be 63.9 meters. Addressing the second question, we are asked, how far does the motorcycle travel during the reaction time? Well, that's going to be phase 1, and so we're essentially asked for the difference between the position at the end of phase 1 and the position at the end of phase 2. Since there is no acceleration, we know that during phase 2, the velocity is constant. So v1 equals v2, which, as we previously determined, is 24.1 meters per second. So we know what this velocity here is at the end of phase 2. To find the position at the end of phase 2, we realize that x1, which was the final position of phase 1, is now the initial position of phase 2. So we go back to our kinematics equation here for position, and we put in the relevant variable names. Now x final is x2, x initial is x1, the initial velocity is going to be v1, the time is t2, 0.115 seconds, and the acceleration is going to be 0. Well, that then eliminates this final term, and we are left with x2 is 63.9 plus 24.1 times the reaction time, 0.115 seconds. This gives us a final position of 66.7 meters. Taking the difference between these two numbers, we get that the delta x during phase 2 was 2.77 meters. So the motorcycle traveled 2.77 meters during the reaction time. The last two questions involve phase 3. We are asked how long does it take the motorcycle to come to a stop, and if the deer doesn't move, will the motorcyclist be able to avoid hitting the deer? We do not know the time to come to a stop in phase 3, but that is easily solved because we know the initial velocity in phase 3, which was the final velocity in phase 2. So we can once again go to the first kinematics equation. V final equals V naught plus AT. In this case, the final velocity is V3, which is 0. The initial velocity is V2. The acceleration is going to be A3, and the time is T3, what we're asked to find. The final velocity is 0. The initial velocity is 24.1. The acceleration is negative 7.83. That negative sign is highly important because it tells us the direction of the acceleration. Solving this equation, we get that the time to come to a stop is 3.08 seconds. Now we have everything we need to find the final position of the motorcycle so that we can determine whether the motorcycle hits the deer. So once again, we turn to the equation of position and get ready to plug in the values now for phase 3. X final is what we need. The initial position of phase 3 is the final position of phase 2, 66.7 meters. The initial velocity at phase 3 is the final velocity of phase 2, which is 24.1 meters per second. The time to come to a stop is 3.08. The acceleration during phase 3 is negative 7.83. Again, that negative sign is very important. And we multiply that by the time squared. This gives us a final position of 103.6 meters, or to three significant figures, 104 meters. This is just barely enough to avoid hitting the deer. We stop a little bit more than 1 meter short of hitting the deer. Thankfully, the motorcyclist's reaction time was not any longer. Also, presumably, in 3.08 seconds, the deer might be able to get out of the way.